All right. Okay, well, thanks, everybody. This particular talk is the Christie Lecture. The Christie Lecture is an invited lecture every year at the fall meeting of the Northeast section in honor of Dan Christie, who was a professor at Bowdoin College and one of the real principals of a long chapter of the section's history. And so it's a distinguished point in the program. We're delighted tonight to have Stephen Miller, who's on my right. Stephen and I go quite a way back. He's in the large set of people who are junior to me in terms of career, do everything better than me, but are still light enough to pretend I'm a mentor, showing they have better social skills than I do too. So Stephen is at Williams College. You know, sometimes you have that thing way up on a shelf at your house you can't quite reach. All you need to get it is Stephen's CV. If you could stand on that, you could reach it, because he's had tremendous success publishing with students, getting grants, working with people in lots and lots of mathematical areas. Really, the thing that always impresses me about Stephen is the breadth of areas in which he's worked. And if you're active as a referee for journals, especially student-related journals like Involve and some of the MAA journals, you've almost certainly refereed one of Stephen's students. It's really a privilege to have him here. He and I also have a long relationship, trading email about baseball, and in particular, coaching baseball, because we have children about the same age, and when we have frustrations we can't express to the parents on our team and our colleagues at our own institution are tired of hearing about them. We have each other for support.
We're not supposed to express those to the parents?
Well, I've been known. I actually did send an email to my day group team last year to 6 parents saying, if your kids don't behave better, they can't all come to the same game. I got some action. You know, I kind of have tenure as a thing. But it's a delight to have Stephen here. He and I have worked together on several different mathematical projects and athletic projects, and I'm delighted to introduce him as the Christie Lecture.
So thank you. It's a great honor to be here. It's nice to actually see that he does do something academic as well. I know far more about what his kids have been doing in terms of routing. One of the many fields I like to work on, since you brought this up, is sabermetrics. If I ever get invited back in the future, I will talk about the work my college students are doing analyzing 7th to 10th graders Babe Ruth statistics. And my students are smart enough to know, so Professor Miller, the goal of the project is to show that your son was the MVP.
Yes.
They learn at a very, very early age. So what I want to do today is I want to talk about one of my favorite problems in probability, the German P problem. I love it for a variety of reasons. The math is not that involved. The statistics is not that involved, but it has tremendous applications, and it is a wonderful way to bring some concepts to students. And depending on how far you want to push it, and given that it is now almost 8 o'clock, we will not push it into doing extensive algebra. I'll push it more into some interesting statistical issues that arise. Now I just have to make sure that the clicker still works. Okay. So I'm going to assume people are familiar with World War II. I'm not going to go into too much detail. These are 2 different maps, and if you actually click on this, you can get a nice video that goes through day by day, and you can see for a long period of time there's essentially nothing happening. And I was asking my students why, and you know, they had no idea, and then I finally said, it's winter. And then you can see all of a sudden when the spring comes, the offensive, and you can see the German armies advancing very rapidly. So when you look at this, you know, the second one, 1942, you can see just how far the German armies have moved, you know, France, Russia, and whatnot. And so the question is, why were they so effective? One of the great reasons was the way they used the tanks. And so it was extremely important for the Allies to understand how many tanks the Germans had and how they were deploying them, how they were using them. So the big question is, how do you figure out the number of tanks? So one possibility is you just, you know, call up Berlin and say, excuse me, you know, I'm a reporter for, you know, the Financial Times. We would want, no, okay, so that's not going to work. So there are two different methods, the spies and there's mathematicians and statisticians. So when did we first start talking about people as statisticians? Yes. Well, OR got founded with World War II, and in fact, when you talk about linear programming, the program is not in reference to a computer science program, but in terms of a program for military. So I'll say math/stats. I don't know if we gave statisticians a separate name all the way back then. Given that I'm a mathematician giving this talk, we will see that the mathematicians and statisticians actually did significantly better than the spies. And we'll show you how to get these formulas. So just so that I can show my credentials, there are easier tank problems you can study. I was an undergraduate at Yale. We had the Morse tank problem, the only tank in the world with a giant lipstick on top of it. So after battle, you see serial numbers S1 through SK on captured and destroyed tanks. And you want to know, using this information, how many tanks were produced, how many tanks were in the theater. So let's assume that the tanks are numbered 1 to n, that the large tank you see is little m, and you want to come up with some estimate for the number of tanks based on m and k. I was shocked. At Williams, we have a requirement that all of our students have to give a public talk. And I gave this project to one of my students years ago, and lots of resources on the web. And I asked, well, what happens if you don't start off with the smallest serial number being 1? If you ever walk into a gym, 215, 200, people don't always start with 1 if they want to impress people. If you walk into, I was told that there might actually be alcohol later tonight. If you walk into a bar, okay, yes, you might see a tip jar. Will the tip jar be empty when you walk in? No. You want to already start people thinking, oh, people tip. Oh, okay. So what is the natural number to start with? Because of problems like this, companies are now very careful and often will not label things consecutively. Oh, you have 2 customers who have chosen your product. Okay, thank you. I may want to go with someone else. And so there's a lot of information now that's done in terms of trying to hide information and being very careful about what presents are you given. So we want to consider not just numbering 1 through 2 through 3, but maybe starting off at some arbitrary starting point. There are technical reasons why it's convenient to start at 1. If the tanks are labeled sequentially, then you can quickly look at the serial number and get an idea of when was it made. Is this tank ready for certain replacements?
Sorry, I was going to say, but if you're thinking about tanks, you also want to know where they're made.
Yes, and so what you could do is you could actually have your serial number broken into different segments, and this, exactly, very similar to Social Security numbers. All right, so there are dangers of overestimating and underestimating. So this is supposed to be a participatory talk. Can anybody give me a danger of either underestimating or overestimating?
I'll do underestimating.
Okay.
It's easier. If you underestimate, you might attack a force that's much stronger than you thought.
Yeah, so you might say, we think there's 10 tanks there, we'll send in 40 tanks, that should be enough, and you say 200. All right, so that is a danger of underestimating. Overestimating. Exactly, and so if you think that there's 1,000 tanks there, and you put in 2,000 tanks to fight it, oh, there were only 6. Then you lost the ability to make progress in other theaters. There's also other dangers of over and underestimating. There's many different paraphrases of this. I love this from the Civil War. If General McClellan isn't going to use his army, I'd like to borrow it for a time. So McClellan was always convinced that however many soldiers he had, Lee had that plus some factor more, and was always afraid to engage. And there is a real danger in not reaching the field of battle. All right, so today I want to just talk a little bit about the preliminaries, talk a little bit about the original formulation. Given that this will bring us to after 805, I don't want to go into how the algebra gets more involved for the new version. It is in the appendices, it is online, so you are welcome to just go there or just send me an email. And then I really want to focus on one of the things I've been doing with this in a bunch of my classes is what are the math and stats issues that arise when you try to teach this. And so there are a lot of good research questions. There's some other things that you could look at if anybody's interested. Happy to chat more over this. All right, so the mathematical preliminaries, assuming everybody knows the factorials, n factorial is the number of ways to arrange n objects when order matters. N choose k is the number of ways to choose k objects from n when order doesn't matter. And the binomial theorem, x plus y to the n, is the sum of n choose k, x to the k, y to the n minus k. All right. Pascal's triangle, which hopefully everybody has seen numerous times. The big identity is Pascal's identity, that n plus 1 choose k is n choose k plus n choose k minus 1. And so the reason we're able to make so much progress in the German tank problem is that we have certain identities that allow us to convert sums to closed form expressions, which means we can see parameter dependence and we don't have to do simulations. Given that a lot of this was from a time when computers weren't that widespread, it's nice not to have to do large-scale simulations. All right, so just to have some proofs, and because I know who was inviting me, we will assume we have n Red Sox fans, and sadly one Yankee fan got through the screening and is at the conference. Oh, okay. Oh. Hey, there we go, okay.
This section's a little too big.
So imagine, so this is proof by story. So here's the proof of story of Pascal's identity. So imagine you have n Sox and one Yankee fan, and you want to choose k people. Well, by definition, it's n plus 1 choose k. And you can break it up into two cases. You're in the fortunate case where you don't have the Yankee fan, and you have k Sox fans. Or, unfortunately, the appeal was acted on by the court, and we were told to be more inclusive. And we will now have the Yankee fan with us. So we choose the Yankee fan, choose one way of doing that. And then we have to choose k minus 1 Sox from the remainder. What's nice is when you look at this, you have a better sense of why Pascal's identity is true. The tops are always summing to n plus 1. The bottoms are always summing to k. There's really two factors of 1 over here, but we're not going to really write times 1 times 1. Right. So there's a lot more identities from Pascal's triangle. If you go along a fixed diagonal, 1 plus 2 plus 3 plus 4 plus 5, that's 15. 1 plus 3 plus 6 plus 10 is 20. So there are more identities like that, and that's the one we're going to use. Other things I often talk about with my students is if you color the dots, if you color the odd numbers and delete all the even ones, you actually get nice fractals. And so I'm not going to go into that now, but there are links over here for some animation to see stuff like that. I wasn't able to find anybody who had written the code for this, so I wrote a really bad Mathematica code, and that's why the triangles are oriented this way rather than the normal way, because it was just easier. Do you have good code?
No, there's no problem. But there was a project in Maryland, Salisbury University, where they wrote a whole program to do exactly this for general.
Oh, if you could send me the link for that, I would love it.
Yeah.
So, I mean, the code I have is kind of like the beginning of Star Wars, where you see the Superstar Destroyer, coming in as it expands out like this. All right. So here is the identity I alluded to a moment ago. This is why the miracle happens. It's this identity that gives us the closed form expression. M choose k m goes from k to n is n plus 1 choose k plus 1. So to prove this, we're going to prove by induction. So we'll fix k. If n equals k, there's nothing to prove. There's only one term on the left, it equals 1. There's only one term on the right, it equals 1. And then this is just a follow your nose, standard inductive proof. Write down the sum at n plus 1, and notice that the first n terms by induction, you already know what it is, and then you use Pascal's identity and you're done. Okay. So now it's time for real audience participation. All right. How should n hat, our best estimate for the number of tanks, depend on m, the maximum observed tank serial number, and k, the number of tanks observed? Does anybody have anything that is even slightly useful for me? Yes, thank you.
N hat has to be bigger than m.
Almost, so close, so close. Yes, greater than or equal to m. Okay, if it has to be greater than or equal to k, so we've got two facts. So we know n hat has to be at least m. I did not see that, by the way. You're welcome. What happens as m goes up? What do you think that should do for our estimate of n? You think our estimate should go up with m or down with m? Up. And if we fix m and let k go up, what do you think should happen to our estimate? Up or down? Down. So what I love about this is when I'm talking to my students, this is where, can you give me some sense of what you expect the answer to be? So what's the simplest formula you could think of that might work? Yeah, and so we'll guess, we know there has to be an m. Let's guess the extra pieces, m over k. And I'll put in some constant b to just give myself some freedom. The actual answer is the constant seems to be 1 and you have to subtract 1. And I'd love to do like the Indiana Jones, with the Nazi with the thing burned on his hand, you have to subtract 1 and give some explanation like this. But sadly, most of my students have never seen Indiana Jones. So I know it is sad. Out of curiosity, how many people remember the Dukakis tank problem? I was wondering if I could do that in this talk, and I figured that there's almost no chance of people getting the Dukakis tank problem. So the next question I always ask, is this a reasonable, if you don't know what the Dukakis tank problem is, research this. It is a classic example of how you have to be careful nowadays in political campaigns. Is this formula reasonable? How can we test and see if this formula is reasonable? Are there any cases we know what the answer should be? Any choice of k where we know what the answer is? Yeah, if k equals n, then m has to equal n because we've observed every tank. And notice that if we do take k equals m equals n, we get back n hat equals n, which is good. There's one other value of k where we have an idea of what the answer should be. What's that value? 0, no. 1. So if there's only one observation, what would you guess if you observe m? It's the mean, and so you would probably guess it should be twice. And so when you put in k equals 1, you basically guess that the number of tanks is essentially twice what you observed. So the formula at least looks reasonable. Okay, and so we did the sanity checks. So the next thing is how to prove this. So let's let big M be the random variable of the largest serial we observed, little m is the value, and we want to calculate what is the probability that we observe little m as the best. And depending on which way you like to do probability, there's two different stories you can tell. You know, the first story is, well, we have to choose k tanks. There are n possible tanks, so there are n choose k ways of choosing tanks. All right, that's the bottom. Here, this is all the ways to choose k tanks such that the largest serial number is at most m. This is how many ways to do it so that the largest serial number is at most m minus 1, so the difference would have a larger serial number of exactly m. If you don't like that, here's the other way of doing it. I know my largest serial number is m, and now I have m minus 1 remaining numbers, and I choose k minus 1 from that. This also gives you a more violent way of proving Pascal's identity through, tank counting. Okay, and so now we just do the definition of the expected value. So the expected value is just each value times the probability it occurs. So we just substitute, and now it's algebra time. All right, so you just plug in what are the factorials. It's algebra time, yes? Yes, right? Yeah, exactly. All right, here. I wasn't going to do this, but since people seem to be excited about algebra, all right. Do people know what a standard Rubik's Cube looks like? Yes. All right. So here's a non-standard Rubik's Cube. Okay? So, if you try to turn the red side, it doesn't work. Try to turn the blue side, it doesn't work. But if you learn to hold it at a 45-degree angle, then you realize this is actually the front side, and the other sides, turn very similarly. And so if you look at it the right way, it's actually essentially the same cube as a standard 3x3. And so when I'm teaching this to my students, the point I always want to try to make with them is, how do you look at algebra the right way to see what to do? And eventually you start to see, well, if I've got binomial coefficients, can I somehow use a formula to evaluate the sum? Or can I expand them out and maybe have some things cancel? And so when you expand everything out, I'm sure everybody by now has carefully looked through all the steps, and you move the stuff that doesn't depend on m outside the summation. And the art of a great talk is foreshadowing. We've already seen that identity. We substitute in for what it is. And that's the miracle. That's what allows us to get the nice clean answer. We then substitute what that is in terms of factorials. And you see that there's almost perfect cancellation, and only a little bit is left over. So we have a formula for the expected value. It's just going to be k n plus 1 divided by k plus 1. All right, well, we can rearrange this. And then we get that our best estimate for the number of tanks is just the observed largest serial number times 1 plus 1 over k minus 1. And so that's the proof of the original tank problem. So if we want to do the new version, which we don't, but if we did, how would it go? Well, we would expect it should depend now on the spread. We have to be a little bit careful because if the spread is 3, there's actually going to be 4 tanks. So if the lowest serial number is 2 and the largest is 5, 5 minus 2 is 3, but there's actually 2, 3, 4, 5. So how do you think the formula is going to be depending over here? Well, probably very similar. But I have a k minus 1. Why do I have a k minus 1 and not a k?
It's the same thing as that if you have that minus n1 plus 1 is really minus n minus 1.
Okay, so there's definitely a plus 1 from here, but I've got my best estimate for the plus 1 over here. This plus 1 is going to be floating around maybe someplace else. But why am I dividing by k minus 1 and not k? Because what you're saying is a good start, but that's going to be independent essentially of the spread. Yes.
Because you already used up your guess.
In what sense have I used up my guess?
He's on his way to being a great mathematician.
Well, but for this, we don't need a great mathematician. We need a so-so statistician. So do we have any so-so statisticians? It has to do with degrees of freedom. If you have one observation, can you estimate a population mean? Yes. What if you observe a 93? What would you estimate for the population mean? 93, right? What would you estimate for the population variance? Okay, so no one's going to be hired by industry. Yeah, what would you like it to be, right? No, but you should not be able to make an estimate on variance with just one observation. So when k equals 1, we should not be able to do anything with a spread because there is no spread. And so k minus 1 is actually very natural here. And so we get S1 plus 2 over k minus 1. And I like the 2. There's a nice interpretation. When we only have the takes going 1, 2, 3, 4, we have one direction which is fixed and one direction we don't know. Now we have two directions. A 2 is a very natural thing to have there. You can do the sanity checks again. So there's a lot of great stuff on the teaching front for this. If anybody is aware of this being done anywhere, I would love to know. We haven't sent this off to a journal yet. And again, if people are interested, there are other generalizations I have of this problem that I think are worth investigating, and would be happy to chat with people afterwards. All right. So I don't want to go through the details here. You don't want to see them. We're all on the same page. You can do something very similar and write down what is the probability for the spread, and then do all the calculations. The algebra is a little bit more involved, but not terribly so. Okay. So when I first started giving this talk, I didn't bother blanking out the German records column because there's really no surprise that the math stats people did better than the spies. I'm giving the talk. But I will have some level of suspense as to just how much better did they do.
The intelligence community has a reason to be off in the direction that they're off.
The same reason why you said how much do you want the variance to be.
Yes, and so, again, this is sort of like the, when you're building the bridge or the elevator in terms of what's the maximum safe, load. It's better to err in certain directions than others. Oh, right. So, but when you have finite resources, you do want to allocate them as efficiently as possible. And so there's a significant factor difference between the numbers. And what's nice is when you win the war, you sometimes get to access records and whatnot afterwards. And when you look at the German records, and this is from Wikipedia, so it must be correct. Because it's been up there for several years. Consistently edited, not just once. People keep changing it. Actually, I am a politician. I am an elected member of the school committee, and I have successfully passed multiple times the ethics test, which I can talk to you about afterwards for $49, because over that I'd have to declare it. So, if you look at the German records, they were pretty much in line with what the statisticians were doing. And one of the big problems is, well, during the war, how do you know whom to trust? And again, it's not enough to have the right answer. And you have to be able to convince people to go with your answer. Okay, so now, yes? I don't know. The other thing is the number of data points we have is so small that the fluctuations, now, one might ask, why is Wikipedia only presenting 3 months? I've done stuff with my students where I'm doing some baseball analysis, and I will randomly select, certain seasons, maybe the Red Sox, maybe 2004. And so I would love to see a much better, more detailed analysis month by month by month. How good is it? But you'll get it's Wikipedia, so it's. So what I want to do for the last bit of the talk is discuss some interesting problems in regression, and I'm hoping there are some people in the audience who might be able to educate me a little bit in some of this. So there are 3 standard ways to try to find, the best fit line or the best fit curve. E1, E2, E3. So I believe y is linearly related to x. I believe it's ax plus b. I observe values x1, x2, x3, x4, and from that, I also observe the corresponding values y1, y2, y3, y4, and I see how good the fit is. So can anybody tell me something that's wrong with E1? Yes. Yeah, if you have a data point at the bottom left and the upper right, if you want to find the best fit line, you could actually draw the line going like this, and the positive error here cancels with the negative error there. So because 1 is a signed quantity, 1 is right out. Okay, what about 2 versus 3? 2, yes. In fact, there's a reason why it's not easily differentiable. It's not differentiable.
It's also not necessarily unique.
It's not necessarily unique. And you have to resort to numerical work to find the best fit answer. Whereas with 3, with 3 though, there's a closed form expression for the best fit values A and B. Now the problem with 3 is large errors contribute more, and it will have, one bad data point will have more of an impact on your best fit parameters, but you have the ability of having closed form solutions. So going back to consulting, I like to tell my students, if I'm the consultant, I argue for 3. If I am the employer, I argue for 2. And so just explicitly writing down the closed form solutions, in terms of the data, is not so bad. And then a lot of relations are not linear. And so if we have something that's not linear, by taking a logarithm, we can often convert it to linear. The example I like to use is earlier today, I was in one of the talks and somebody was mentioning work about Kepler and results that were done on the elliptical orbits. I think it was 30 years before Kepler. The one I want to do is the third law, which is the square of the period is proportional to the cube of the semi-major axis. This is very similar to the Euclid fifth talk, where all the other axioms are nice and simple, and this one is far more involved. How could you sniff out a relationship like this? Well, because I'm calling it b tilde, almost surely that's not the constant I care about. If I just take the square root of both sides, you can always normalize, so the exponent of t is 1. And so the question is, how would you find that exponent of 1.5? Well, if we take logarithms, we will now have a nice linear relationship. And so here's the data for the planets. I am sad to report Pluto is no longer on this list. But with the 8 planets we have, you can still put Pluto, of course, as just an astronomical object. Things are normalized nicely, so we have distances in astronomical units and periods in basically years. So you'd expect this constant b should be very close to 1. And so there's a whole slew of fun units in science and society. The Bruno, the millihelen, the slug, the Smoot. Has anybody heard of any of these? The Smoot. The Smoot is the most famous of them. The slug is actually used in some science. The Bruno and the Smoot are both MIT units. I will mention the Smoot a little bit later. The millihelen, I think the millihelen is famous. I first learned about that from an Isaac Asimov thing. So if we look at the plot, you can see it's almost perfect. And so you get the best fit parameter for the slope is 1.49986. That's pretty close to 1.5. If b, capital B is supposed to be 1, the log of 1 is 0. You get very close to 0 as well. And so now I will just mention briefly Smoot. So a lot of people seem to know who Smoot is. Who is Smoot?
He was a student.
He was a student where? At MIT.
And they rolled him across, and that's the mass average.
Yeah. Oh, oops. Oh, ooh, bad typo. Thank you. No, wait. Yes. Yeah. Boston is a city where you can have 2 votes cross each other as to which one is above, changes depending on where you are. But, it's not just academics who have research questions. Fraternities have research questions too. And one of them was, how many Smoots does it take to cross the bridge? And so they discovered it's 360 people, and I love this, plus or minus an ear. And so they picked him up, marked, picked him up, marked, picked him up, marked. Cambridge thought that this was not funny, and they had the markings erased. MIT, the fraternity thought that this was terrible because this is science, and they put the mark, and they went back and forth, and now it's been institutionalized, and when there's an accident on the bridge, they actually have Smoot markers, and they report the accident based on how many Smoots. Now, if you know the answer, please don't give away the punchline. Does anybody know what happened to Smoot? Oh, good, excellent. So if you say, okay, one person knows. So if you stay awake till the end of the talk, or just wake up at the end of the talk, you will find out what happened to Smoot after an interesting beginning to his college career. So for those of you who are in college, well, all right. I'm going to skip the birthday problem for now because it's getting a little bit late. Here was my first attempt of doing regression for the German tank problem. And I said, well, I know there has to be at least m tanks, so let me look at n minus m. That's the excess of how many tanks there are based on what I observe, and I'll plot it against m over k. And it sucks. That's, I think, a technical statistics term that you learn in grad school. If you do a two-dimensional plot, if you do logarithms and you plot the log of n against the log of m and 1 over k, you actually get a really nice planar fit, and the statistics looks really good. But what I want to do for the last bit of this talk is describe how you could actually sniff out the relationship 1 plus 1 over k times m just by doing some data analysis and just by doing some simulations. So rather than doing all this theory, if you don't know enough to see how the algebra is done, could we still conjecture this relationship in the data? Right. So implementation issues. So here's a plot of n, the number of tanks, versus the observed maximum number for k equals 1. So theory predicts it should be 2m minus 1. The best fit line is 0.784m plus 2875. There's many things wrong with this best fit line. Which offends you the most? I know, I mean, we're doing this for the German tank problem. It should be a gray, it should be an axis written. All right, so one is the color. What else offends you? Is that? Yes. Okay, what else? Something bothers me more than the y-intercept though. Yeah, the slope. What's bad about the slope of 0.784? Yeah, it should be at least 1. Yes. So when I ran this in Mathematica, I was not thrilled that this was the best fit line that it was coming up with. I tried k equals 2. Best fit line has a slope of 1.5. This is getting 0.964. It's bad, but it's at least not as bad. Getting up to k equals 5, you're at least getting a line that now at least has a slope greater than 1. But it's still not great. So I tried doing it the other way. I tried plotting the observed value m versus n. And now the best fit line should be 0.5n plus 0.5. And doing it this way, I actually got a pretty good slope of 0.496. So if there's a real statistician here who would like to explain some of this stuff to me, I would love to know a little bit more about stuff like this. It gets a little bit better with using k equals 2 or k equals 5. Another nice trick you can do is you can average. So do 100 simulations for each choice of n and put a dot. And when you do that now, you get a best fit line of 1.5 minus 1. Oh, this is probably k equals 2, not 1. Sorry. And you get 1.496. So again, it's working pretty nicely like this. So the last thing I want to end with is here is a plot of the slope versus the number of observations versus k, how many tanks I observe. And so we believe that n is equal to 1 plus 1 over k times m minus 1. All right, I don't really care about the minus 1, that's insignificant. I really want to understand this 1 plus 1 over k factor. And so for each value of k, I do some simulations and I report what is the best value of the slope in the best fit line. And I record that and I get a plot like this. And it's kind of hard to understand a plot like this. So the question is, how can we transform this data and sniff out the relationship? Well, we'll do a log-log plot. And because we have a reason to believe that if you observe the largest serial number of m, there should be at least m tanks, it makes sense to subtract 1 from your constant. And so instead of looking at the constant a, look at the constant a minus 1, which would be 1 over k. And so when we plot a log-log plot of a minus 1 and we do the best fit line, we get the log of a minus 1 versus log of k. The theory is the log of a minus 1 should be -1 log k. The best fit line is the log of a minus 1 is -0.999 log k. Okay, that's essentially -1 times log k, which is essentially the log of 1 over k minus bond. All right, so I don't know in all the different reversions as to when he actually began. I don't know if he was really active in World War II. I think he started later, but you know, that doesn't seem like a terrible number to have there. But the fact that we're getting a log of a -log k is wonderful. Is that just looking at this data, we can sniff out the relationship. All right, so a couple of references, but first, the advice and the promised end. So I always tell my students to seize opportunities. You never know where things will lead. So yes, they may be hazing you as you are pledging the fraternity, but maybe it'll all work out for the best. So this is what Smoot looked like later in life when he wasn't being used as a unit of measurement. You can't make this stuff up. And again, I checked it on Wikipedia, so I'm pretty sure. He became the chairman of the American National Science Institute. And so as my students are preparing for interviews, I always tell them, you want to adjust things to focus on your strengths. And I can just mention, well, I don't want to brag, but I am a unit of measurement. I taught a class at Williams years ago on cryptography, and I encrypted the title. And the registrar was like, you know, we can't yes, you can. You know, it'll be a conversational starter. And several of my students told me that, you know, when they were having job interviews, people said, I got it, what is that you took? So thank you.
Professor Christie really enjoyed that. Any questions?